Now let's look at a situation where we want to figure out what's going on with a curved gate. This gate is a circular arc, quarter of a circle in this case, and it's holding back the water behind it here, 3 meters deep, and the radius of the circle is 4 meters. And we need to exert a large enough force F here to keep this gate from, again, tipping over this way. The fact that this is a circle makes the geometry that much more complicated and is going to make it a little more difficult to do the calculation. But the idea is still the same. The moments about that pin joint must be equal to 0 if it's not going to move. So the sum of the moments about A must be equal to 0 for equilibrium. So once again, applying all the concepts of free body diagrams, we're going to have to match up that FR, because pushing up with force F here at a distance of 4 meters, that's R, away from this pin, is going to be tending to move in that direction around the pin joint, must be equal to the sum of the moments due to the water. Now, as we go around this curve, we're going to have pressure acting always perpendicular to the surface. So we're going to have to resolve this in terms of both X and Y components. So if I took a little chunk of surface that might have that slope there, I've got a pressure force acting on it. It's going to be equal to negative n, where n is the unit normal vector, times p dA. I'll have to think about the projected areas in the X and Y directions to break that into component forces in X and Y to be able to manage my system a little more easily. So if I look at that system, well, it's going to be pressure acting over this area in the downwards direction, so a little chunk like that, and another chunk acting over a surface projected in this direction like that. So this is P times dx, because that dimension there, that's dx. This dimension here, that's dy, and we're able to break that out from the combined pressure acting over this area here, which is equal to the change in length along the arc from A to B times the width W, which we're assuming is 1, into the page. So we'll wind up with F times R acting in that counterclockwise direction equal to the integral from A to B, so over this entire surface here where the water is acting on the surface, and we'll do the chunk due to the X force first, this one, the one that's over the differential area X. We'll have P times dx, that's the force that's acting downwards onto the projected area on the x-axis. And if we've got a force acting downwards here and it's offset just a little bit over this way from A, then the location that it's at, the radius out from A, will be equal to x plus 4. So this is the force, and this is the moment arm. So when x is equal to negative 4, it's equal to 0. There's nothing going on. As x gets to be a little larger, a little smaller negative number, then this will go to be slightly larger than 0. So that's due to the force components acting downwards. Now we need to account for the force components acting horizontally, these ones. So integral from A to B, the moment arm, well, it'll be just equal to y. It's whatever height we are above A. So there's our moment arm, y, times the pressure, times dy. And the two of them combined together account for the fact that we've got surfaces facing in different directions as we go along that arc. Now rearranging, we've still got integral from A to B, x plus 4. The pressure, well, it'll be rho g times the depth under the water, which will be 3 minus y. So we've got y in this integral as well as x times dx plus the integral from a to b of y times rho g times 3 minus y dy. But we've got y is a function of x, or x is a function of y. So we're not going to be able to get away with just having that y in there. We're going to have to sort that out. X squared plus y squared equal to 4 squared equal to 16 is the equation of that circle. And it applies on that gate and also the whole circle that goes all the way around. So we'll from there be able to say that y is equal to 16 minus x squared square root. And locations A and B, we're going to need to define those as actual numbers in order to be able to solve this problem with these limits of integration appropriately. So at location A, we're over here. Well, x is equal to -4. That's easy. And y is equal to 0. And at location B, it's going to be a little more complicated. Y is equal to 3. And we'll then have to figure out, well, if that's 4 and that's 3, then what's this location here? We'll wind up with x equal to negative square root of 7, plugging in here. So reversing the equation to figure out the corresponding x value. So we'll wind up with F times R, the force and moment arm combination required, equal to the integral from a to b, and we're going over x, so we're going to go from -4 to negative square root of 7. That's the range of x, times x plus 4, the moment arm, times rho g, times 3 minus y. But y is a function of x, so we better get that into our integration. 3 minus the square root of 16 minus x squared dx. So there's our first integral. And then the second integral will be going over y, so the integral from y equals 0 up to y equal to 3 of y times rho g times 3 minus y dy. Now, we could probably do this integration, even though it looks a little complicated, if we went back and dusted off our calculus skills. But at this point, I'm going to say that even for this simple case, I'm going to go to a numerical integration, because I know I can do that more quickly with the tools I've got available, and that I'm more likely to get the correct answer. So in exams, the major thing that we're going to be looking for is that you're able to set up this kind of a problem, that you're able to recognize that you've got two dimensions here, so you've got two directions to consider those pressure forces over, and that you understand that you're going to wind up with two separate integrals. So we will not be examining you on your ability to do more complicated integrals than the simple ones that we've done of simple ordinary polynomials.